The speed of light is supposed to be the final limit. But what if you went beyond it? And what would that do to everything you think is possible? If you enjoy watching these type of videos, subscribe to the channel. Let's begin. You were taught that speed is something you can always increase. More power, more fuel, more thrust, more motion. That idea works almost everywhere in normal life, and it works so well that it feels obvious. But physics says there is one speed that does not behave like the others. In empty space, light moves at 299,792,458 meters per second, about 186,000 to 282 miles per second. And in modern physics, that number is not just the speed of light, it is the speed limit built into space-time itself. So when you ask what happens if you go faster than light, you're not asking a simple question about travel. You're asking what happens if something crosses a boundary that physics treats as fundamental. And that is where the first misunderstanding has to go. This is not really about light in the everyday sense. The phrase speed of light makes it sound like this rule belongs to photons, like it's just a property of beams, lasers, and stars. But the deeper idea is bigger than that. That speed is built into the structure of reality. Light travels at that speed because light has no rest mass. Matter does not. So the real question is not whether you can beat a ray of light in a race. The real question is whether anything made of matter can cross the line that separates normal motion from something physics does not know how to handle in a stable way. That already sounds extreme, but this is not just theory. We have tested this limit with real machines. Particle accelerators have been pushing matter to absurd speeds for decades. At CERN, protons in the Large Hadron Collider move so close to light speed that the gap is tiny, only a few meters per second below the limit, even though the energy involved is enormous. That matters, because it shows something very important. As you get closer to light speed, adding more energy does not give you a normal increase in speed. It gives you less and less return. The universe does not act like an open road. It acts like there is a hard boundary ahead. And your intuition is not ready for that, because your intuition was built at low speed. At car speed, Newtonian physics works well. At aircraft speed, it still works well. At the speed of a bullet or a spacecraft returning through the atmosphere, classical physics is still good enough for most practical purposes. In that world, time is time, distance is distance, and motion feels simple. But once you move into a serious fraction of light speed, that whole picture starts to fail. Time does not stay universal. Distance does not stay fixed. Even the order of events starts depending on who is observing them. So the moment you start talking about exceeding light speed, you're already outside the zone where common sense can guide you. And that raises the stakes fast. Because if faster than light travel were only about getting somewhere sooner, this would just be an engineering problem. Better engines, better materials, bigger power sources, but that is not what is at risk here. If matter could move faster than light, then cause and effect could start breaking in a serious way. One observer could say event A happened before event B, while another could say the opposite. And if information can move faster than light, that can lead to situations where an effect shows up before its cause. That is not just strange, that is the kind of problem that can make a physical theory stop making sense. So the question sounds simple, but it is not simple at all. It starts as a question about speed, then turns into a question about time, then into a question about causality, and then into a question about whether reality can stay logically consistent. That is why physics treats this line so seriously. Light speed is not just one more benchmark on a scale from slow to fast. It is the dividing line between the part of the universe where our normal ideas still work and the part where those ideas begin to collapse. Then the next question becomes unavoidable. If the universe is so strict about this limit, why can anything get close to it at all? Why do particle accelerators push matter almost all the way there? And why does physics allow that approach, but not the crossing? That is where the problem gets even harsher, because the closer you get to light speed, the more energy you need, and the increase does not stay manageable. It grows so fast that the idea of just add more thrust stops meaning anything. That is the first real warning sign. In ordinary life, more energy usually means more speed. Near light speed, that relationship breaks down. You keep paying more and you get less back. The closer you get to the limit, the more extreme the cost becomes, so before you even ask what happens beyond the speed of light, you hit a more immediate problem. Physics makes reaching that line itself look almost impossible, and that is exactly where the tension rises. Because if approaching the limit already forces time, energy and motion to behave in ways that feel unnatural, then what happens next when you get even closer? And why does the energy cost start exploding so badly that even our most advanced machines can only crawl toward the boundary instead of crossing it? The next problem is simple to say and brutal to deal with. Why does speed get so expensive when you get close to light speed? Because at low speed, your instincts still work. Push harder, go faster, burn more fuel, gain more speed. That is how motion feels in normal life. But near light speed, that relationship starts breaking down, and then it breaks down completely. The closer you get to C, the more stubborn reality becomes. In special relativity, the kinetic energy needed to keep accelerating does not increase in a calm, predictable way. It rises sharply, then violently, then so badly that the whole idea of just adding more thrust stops making sense. Start with 10% of light speed. That is about 29,979 kilometers per second, or 18,628 miles per second. Even that number is already far beyond anything human beings normally deal with. At that speed, you're not talking about a fast missile or a fast probe, or even a fast escape trajectory from the solar system. You're talking about motion so extreme that Earth would look small almost instantly. But 10% of light speed is still nowhere near the real problem. The real problem begins when you keep pushing. At 50% of light speed, then 80%, then 90%, the energy cost starts climbing much faster than the speed itself. By the time you get to 99.9% of light speed, the numbers become absurd. Not slightly difficult, not technically challenging, absurd. This is where relativity stops feeling like a correction to normal physics and starts taking over completely. The reason is tied to one number physicists use all the time: the Lorentz factor, also called gamma. You do not need the equation to feel what it means. At everyday speed, gamma is so close to 1 that it changes almost nothing. That is why normal physics works so well for cars, planes, bullets and rockets. But gamma does not grow steadily. It stays close to 1 for a long time, then starts rising faster and faster as you approach C. At 90% of light speed, gamma is about 2.29. That already means relativistic effects are not small anymore. At 99% of light speed, gamma is about 7.09. Now the system is deep into relativistic territory. At 99.99% of light speed, gamma jumps to about 70.7. That is the kind of escalation that destroys normal intuition. You're making tiny gains in speed, but the factors controlling energy, momentum and time are exploding. And this is the part people often miss. When physicists say the energy blows up as you approach light speed, they do not mean it becomes a lot. They mean the cost gets worse and worse without settling down. Every extra bit of speed near the limit costs more than the last bit, then much more, then far more. So the idea of just using a bigger engine is not really answering the problem. If the rules of relativity hold, a massive object can keep getting closer to C, but the price keeps rising toward infinity. That means the barrier is not sitting there waiting for good enough engineering. The barrier is built into the math that describes motion itself. And this is not just a theoretical argument. Real machines already show the pattern. Particle accelerators do this for a living. Electrons in synchrotrons, protons in colliders, muons in beamlines, they all behave the same way. Scientists pour in more and more energy, and the particles do go faster, but by less and less. The closer the particles get to light speed, the smaller the speed gain becomes for every extra energy increase. That is why protons in the Large Hadron Collider move only a tiny amount below C, even though their energy is enormous. Cosmic rays do the same thing in nature. Some of them hit Earth's atmosphere with incredible energies, far beyond what human-made machines can easily produce. And yet they still do not cross the limit. So this wall is not a philosophical wall. It is not there because physicists dislike the idea of faster-than-light motion. It shows up in direct measurements. That is why everyday analogies start failing here. In normal life, doubling fuel does not double speed, but at least the result still feels understandable. You know the system wastes some energy. You know drag matters. You know engines have limits. But relativity is not just another efficiency problem. Near light speed, you are not mostly fighting friction or bad engines or weak materials. You are running into the structure of space-time. That is why common comparisons stop being useful after a point. You can say it is like trying to make something run faster with more and more energy, but even that is too soft. The real issue is that the geometry relating space and time is changing what your effort can buy you. So if someone says, why not just keep accelerating until you cross the line? The answer is that the line is not like the sound barrier or a mountain pass. It is not a threshold that becomes ordinary once you break through. In relativity, reaching exactly c is already impossible for anything with mass because doing that would require infinite energy, and that creates a deeper problem. If the math says you cannot even reach the limit with finite energy, then going beyond is not just an even harder engineering step. Inside the same framework, it is not a valid continuation. It is not like saying first you reach the top of the hill, then you go over it. The theory is telling you there is no ordinary path from below C to above C for massive matter. That is why this section matters so much. The speed of light barrier is not just a warning sign. It is not there to tell you the trip is expensive. It is there to tell you the rules are changing in a way that blocks the crossing itself. More energy does not solve that. More power does not solve that. A better engine does not solve that. If you want a massive ship to exceed light speed inside known physics, you are not asking for better propulsion anymore. You're asking for a different universe, and the tension gets worse from here, because energy is only the first thing that spirals out of control. Once you get near light speed, it is not just your fuel budget that changes. Time itself starts splitting apart between you and the outside world. Your clock and the universe stop agreeing, and that is where the question stops being only about motion and starts becoming a question about what speed does to time itself. The next thing that breaks is time, not your watch malfunctioning, not some visual trick, not a mistaken measurement, actual time. As you move faster, your time slows down relative to people who are not moving with you. This is one of the hardest ideas in relativity because it sounds fake the first time you hear it. In normal life, you expect 1 second to be 1 second for everyone, but near light speed, that stops being true. If you were on a ship moving fast enough, your clock would tick more slowly compared to clocks back on Earth. Inside the ship, everything would feel normal to you. Your heartbeat would feel normal, your thoughts would feel normal, your hand would move normally. But from the outside, the universe would see your time falling behind. And this is not a theory waiting for proof. Time dilation has been measured directly. Atomic clocks flown on aircraft show it. Satellites show it. High-speed particles show it. The effect is real, repeatable, and built into working technology. That matters because it changes the tone of this whole question. We are not talking about a speculative side effect of extreme travel. We are talking about a physical fact that has already been tested many times. So when physics says time starts behaving differently near light speed, that is not a warning about some imaginary future experiment. It is a description of how reality already works. One of the clearest examples comes from muons. Muons are unstable particles created when cosmic rays hit Earth's upper atmosphere. At rest, a muon only lasts about 2.2 microseconds before it decays. That is an extremely short lifetime. If you use normal, non-relativistic reasoning, you would expect many of those muons to decay long before reaching the ground. They are created high in the atmosphere, they do not live long, and the trip down should be too long for most of them to survive. But that is not what detectors see. Large numbers of muons do reach Earth's surface. The reason is time dilation. From our frame, their internal clocks are running slower because they are moving so fast. so they survive longer than normal intuition says they should. This is one of the best demonstrations in all of physics because it is so direct. Relativity is not hidden in a giant machine only experts can access. Part of the proof is literally coming down through the sky. Then there is an example you use almost every day without thinking about it. GPS only works because Einstein was right. GPS satellites orbit roughly 20,200 kilometers above Earth, about 12,550 miles, and their onboard clocks do not stay perfectly synced with clocks on the ground unless relativity is taken into account. Their speed produces special relativistic effects, and their position in Earth's gravitational field produces general relativistic effects. Engineers have to correct for both. If they did not, navigation errors would build up fast, on the order of kilometers per day. So your ability to open your phone and find a cafe or a train station or a hospital depends on the same physics that tells you light speed is not just another speed. That should make this feel much more real. These are not exotic ideas sitting far away in a textbook. They are active corrections inside systems people use every day. Now push that idea to an extreme. Suppose you could travel at 99.5% of light speed, about 298,293 kilometers per second, or 185,354 miles per second. To people watching from Earth, a long trip might take years, but for you on board, much less time would pass. A journey that looks huge from the outside could feel much shorter from the inside. That is where this topic starts becoming seductive because it sounds like a loophole. You do not need faster than light travel to reach the far future. Relativity already gives you a way to do that. Travel fast enough, and while only months may pass for you, years or decades can pass elsewhere. In that sense, the universe already allows one-way time travel into the future. But the catch is severe. You are not skipping forward and then coming back to the same moment you left. That moment is gone. Earth has moved on without you. Everyone else has aged more than you have. History has kept going while your own clock ran slower. So relativity does give you a way to leap into the future, but it does not give you a way to preserve the present. That makes the whole idea feel less like a convenient shortcut and more like a trade. You can reduce the time you personally experience, but you do it by separating your timeline from everyone else's. And this is where the original question gets more dangerous. Once time itself becomes flexible, the issue is no longer just motion through space. It becomes a question about chronology. Below light speed, relativity already lets different observers experience time differently. It already lets one traveller age less than another. That is strange enough, but it still keeps cause and effect under control. Events can stretch, clocks can disagree, journeys can compress from one point of view, and yet the basic order of cause and effect still holds together. That is the key protection. So now think about what happens if you try to go beyond that limit. If moving near light speed already makes your clock and the universe stop agreeing, what would happen if you crossed into faster than light motion entirely? The danger is not just that time would slow more. The danger is that the order of events itself could start changing depending on who is watching. And that is where the problem stops being personal and becomes much bigger. Because after time bends, the next thing under pressure is distance itself, and the universe starts offering something tempting. Distances shrink, but only for you. The next strange thing is that distance stops being fixed, not in the loose everyday sense, not because you measured badly, but because motion itself changes how space is measured. The faster you move, the more lengths contract in the direction you're travelling. This is another consequence of relativity, and it matters a lot once speed gets close to light speed. To someone on Earth, a destination can stay exactly where it always was. A star like Proxima Centauri is about 4.24 light-years away, and that is the distance they will keep talking about. But to you, if you are moving fast enough, that same distance can become much shorter in your own frame. So now the problem gets even stranger. Time has already changed, and now space changes too. This is where relativistic travel starts sounding almost like a loophole, because if the distance itself shrinks for you, then a trip that looks huge to outside observers can feel much smaller from inside the ship, and the effect gets extreme fast. At 99.99% of light speed, gamma is about 70.7. That means distances in your direction of travel are contracted by that same factor in your frame. So a journey that looks like years from the outside can feel dramatically shorter for you. Not because you secretly went faster than light, and not because the destination moved toward you in the normal sense, but because the way your frame measures the distance has changed. That is what makes relativity so hard to absorb. You're not just moving through space, the amount of space you have to cross changes depending on how you are moving. And this is not a science fiction trick. It is part of the same relativistic framework that modern physics uses everywhere high speeds matter. When scientists analyze particle beams, relativistic effects are essential. When astronomers study jets from active galactic nuclei, pulsars, or gamma-ray bursts, relativity shapes what we observe. The same mathematical structure that gives you time dilation also gives you length contraction. So this is not a side idea added for drama. It is built into the same theory that keeps matching experiments and observations across both the lab and the cosmos. That matters, because it means the shrinking of distance is not optional. If you accept the rest of relativity, this comes with it. And this is exactly where people try to force a loophole that is not really there. The argument sounds tempting. If the distance gets small enough in your frame, then maybe you have effectively beaten light speed. Maybe you did not need to go faster than light after all, because the trip became short enough that it feels like the same thing. But that is where you have to be careful. Length contraction can make a journey subjectively shorter, but it does not let you exceed c locally. At every point along the trip, your local speed relative to nearby spacetime is still below the limit if you're a massive object. So the universe gives you something remarkable, but not everything. It lets the trip feel shorter to you, but it does not let you break the causal speed limit that keeps relativity consistent. That is the compromise built into the system. From your point of view, the road can shrink. From the outside, the ship still never outruns light. Both descriptions are real inside their own frames, and both are consistent with relativity. That is why this topic is so easy to misunderstand. It can feel like you have found a way around the rule, when really you have only found one of the weird ways the rule expresses itself. You're not escaping the structure of space-time, you're seeing how deeply that structure controls both time and distance. And psychologically, this is where the trap gets stronger. If you were on that ship, it would absolutely feel like you were getting away with something. The destination would arrive sooner than it should. The time on your own clock would be shorter than people back home expected. The distance ahead of you would seem reduced. Everything about the trip would feel like reality were bending to help you. But from the outside, no physical law was violated. No one saw your ship cross the light barrier. No observer had to give up the basic rule that matter stays below c. So relativity gets very close to giving you the dream, fast access to distant stars from your own point of view, and then stops right before the one step that would actually break causality. That should tell you something important. Physics is not refusing to be weird. It is already being very weird. Time slows down, distances shrink, journeys compress from the traveller's point of view. The universe is already allowing effects that sound shocking at first hearing. And yet even with all that flexibility, it still protects the boundary. That should make you suspicious of any easy faster-than-light claim, because relativity already gives you the maximum amount of weirdness it can tolerate without losing control of cause and effect. And now the next mistake becomes impossible to ignore. If time can slow down and distance can shrink, then people naturally start saying something else. Maybe the object itself changes. Maybe its mass increases. Maybe that is the real reason the barrier is there. But that leads to one of the most misunderstood parts of this whole topic, because the mass problem is real, just not in the way people usually think. A lot of people think they already know the answer here. Objects get heavier as they approach light speed. You've probably heard that before. It shows up in pop science, old textbooks, and a lot of casual explanations, and it is not completely useless, but it can mislead you badly if you take it too literally. In modern physics, we usually do not say an object's mass increases as it speeds up. Its rest mass, also called invariant mass, stays the same. What changes is its total energy and momentum, and that difference matters, because the real problem is not that the object is turning into some heavier version of itself. The real problem is that the relationship between force, motion, and energy stops behaving the way Newton taught you to expect. That older phrase, relativistic mass, stayed around for a reason. It was a way to explain why pushing a fast-moving object gets harder and harder. It captured something real about the growing resistance to further acceleration. If you push something moving very fast, you do not get the same response you would get at low speed. So saying it acts like it has more inertia was a useful teaching shortcut. But the more precise modern view is better, because it keeps the language clean. The object itself does not quietly gain a new rest mass as speed rises. Instead, the energy and momentum you have to deal with start increasing dramatically as the speed approaches c. That may sound like a technical preference, but it changes how you think about the barrier. If you say mass increases, it can make the whole issue sound like a difficult mechanical problem, like something with enough engineering might eventually overcome. But relativity is telling you something deeper. This is not just about a machine struggling to push a heavier load. It is about the structure of space-time setting rules that do not let a massive object cross that boundary in the first place. And the evidence backs the modern view extremely well. In particle accelerators, scientists push particles to huge energies and measure how they behave. What they see matches relativity very closely. Momentum rises exactly the way the theory predicts. Energy rises exactly the way the theory predicts. There is no need to invent some special speed-dependent rest mass to make the data work. The full energy-momentum relationship already explains what is happening. That is one of the reasons modern physics prefers this language. It is not about fashion, it is about using the cleanest description that matches the measurements. When particles are accelerated, their behavior fits the relativistic framework beautifully, and that framework does not require rest mass to change. That becomes even more important when you ask why matter cannot simply cross the speed of light limit. A photon has zero rest mass, and in vacuum it naturally moves at c. Matter is different. A particle with non-zero rest mass naturally moves below c. Those are not just two different speed ranges on one continuous dial. In relativity, they belong to different categories. They trace different kinds of paths through space-time. So going from a massive thing moving below c to a massive thing moving above c is not like shifting into a higher gear. It is not like breaking a speed record after enough upgrades. It is more like asking whether one class of physical object can become a different class entirely. Inside known physics, that is not a normal transition. This is the part that kills the usual intuition. People often assume that if you can get extremely close to light speed, then the rest is just a matter of scale. Maybe you need a much bigger engine, much more fuel, much more time, but eventually you get there. That is how most limits in ordinary life work. A steep hill is still a hill. A hard record is still just a record, but the mass issue shows why that picture fails here. The light speed barrier is not just very high, it is built into what a massive object is allowed to be. As long as the object has non-zero rest mass, relativity keeps it in the below C category. Not because engineers are weak, not because we have not found the right material yet, but because the object's identity inside the theory comes with that restriction. So this section clears up a major confusion. Matter does not need to become infinitely heavy in some loose cartoon way for the barrier to matter. The more accurate statement is sharper than that. Its rest mass stays the same, while the energy and momentum required to keep pushing it rise without giving you a path across C. That is a much more serious problem than just extra weight. It means the barrier is not only energetic, it is structural, and once you see that, the next section gets a lot more dangerous. Because if the limit is tied this deeply to the identity of matter and the structure of space-time, then breaking it would not just mean going unusually fast. It would mean tearing into the logic that keeps events in the right order. And that is where the real threat appears, because faster than light motion does not just challenge motion, it starts to crack causality itself. The real danger is not that faster than light travel would be too powerful. The real danger is that it would break cause and effect. That is the part people usually miss. In relativity, the speed limit is not just about motion. It is tied directly to the order in which events can influence each other. As long as signals and objects stay at or below c, the structure of cause and effect stays consistent across observers. Different people can disagree about details, they can measure different times and distances, but they do not lose the basic rule that causes come before effects. The moment you allow something to go faster than light, that protection starts failing. And once it fails, the problem is not just weird physics, the problem is logical instability. To see why, you have to start with something relativity already says long before FTL enters the picture. Two events that look simultaneous to you may not look simultaneous to someone moving relative to you. That is called the relativity of simultaneity, and it is one of the core features of special relativity. It is not a side note, it is built into the structure of the theory. If two flashes happened far apart, one observer may say they happened at the same time, while another observer moving relative to the first may say one happened earlier. That sounds strange, but it does not create contradictions by itself, because neither flash is causing the other. They are just separate events whose timing depends on the observer's motion. The trouble begins when you add faster than light signaling. As long as signals cannot outrun light, relativity keeps causality safe. The order of cause and effect stays protected even though observers may slice time differently. But if a signal can go faster than light, that safety barrier disappears. Then you can set up situations where one observer says a message was sent first and received later, while another observer says the receipt happened before the sending. That is not a harmless disagreement. That is the start of a real contradiction, because now the event that is supposed to be the effect can happen earlier than the cause in some valid frame of reference. This is why physicists talk about the tachyonic anti-telephone. The name sounds technical, but the idea is simple and disturbing. If faster than light messages were possible, then under the rules of special relativity, you could construct a setup where a reply arrives before the original message was sent, at least in some frame. In principle, that means information could be sent into the sender's own past. And this does not require exotic time machines, spinning cylinders, or wormholes. Just special relativity plus usable FTL signaling is enough to create the threat. That is what makes this so serious. You do not need a whole new fantasy universe to get paradoxes. You get them by combining one accepted theory with one forbidden capability. And once information can go into the past, the usual paradoxes appear immediately. You send a message saying, "Do not send this message." So was it sent or not? You receive an answer to a question before you ask it. So where did the information come from? A warning arrives before the event it warns about and prevents it. So why was the warning sent in the first place? These are not just storytelling tricks. They show that the system stops giving consistent answers, and physics depends on consistency. A theory cannot survive if it allows contradictions at the level of cause and effect. That is why this is more than a philosophical problem. Causality is not some decorative feature added to make the universe feel sensible. It is part of the foundation that lets physical law work at all. Prediction depends on it. Thermodynamics depends on it. Quantum field theory depends on it. Ordinary reasoning depends on it. Causes leading to effects in an ordered way is one of the things that make science possible in the first place. If faster than light motion lets events trigger themselves retroactively, then you have not just made transportation faster, you have damaged the framework that lets events have a stable sequence at all. And this is where the original question starts to break down at the language level. When you ask what happens if you exceed the speed of light, the sentence assumes there is a clear before and after. It assumes there is a clean order to events. First you cross the line, then consequences follow. But if faster than light motion allows time-ordered reverse for some observers, then even that simple structure stops being secure. The word after becomes frame-dependent. One observer says event A caused event B, another says B came first. And once that happens, the question is no longer just hard to answer. It becomes partly malformed inside the theory itself. That is the most unsettling part of this entire topic. The horror is not that reality would explode in some dramatic visual way. The horror is quieter than that. Reality could stop agreeing with itself. Different valid observers could assign different time orders to the same chain of events. And if information is allowed to outrun light, those disagreements can become contradictions instead of harmless differences in perspective. So the barrier at sea is not only blocking speed, it is protecting chronology. And that should raise a new question immediately. If going faster than light creates this much damage, then maybe the only way out is to ask whether there are things that were never trapped below the barrier to begin with. Not ships pushed too hard, not matter crossing over, but something that might naturally live on the other side of sea from the start. That is where one of the strangest ideas in physics enters the story: tachyons, the hypothetical particles that were supposed to save the idea and may only make the problem worse. So maybe the escape route is this: what if some things were never below the barrier in the first place? That is where tachyons enter the story. Tachyons are hypothetical particles that would always move faster than light by their very nature. Not ordinary matter pushed too far, not a spaceship crossing sea after some impossible engine upgrade, but a completely different kind of particle that starts on the superluminal side from the beginning. In that sense, they are the mirror image of photons. Photons, which have zero rest mass, naturally move at sea in vacuum. Tachyons in the old speculative picture would naturally exist beyond sea and never slow down below it. That is why the idea attracted so much attention. It looked like a way around the infinite energy barrier, because the particle would not need to be accelerated through the forbidden line at all. And on the surface, that sounds clever. If the problem is that matter cannot cross the speed of light boundary from below, then maybe you avoid the problem entirely by starting with something that was never on that side. That is the appeal. But once physicists started taking the idea seriously, the picture became much less friendly. Tachyons did show up in theoretical work, and that is important. This was not a throwaway fantasy that nobody in physics ever touched. The concept was analysed, formalised, and tested against real theory. But the way tachyons appear in modern physics is usually not the way pop science presents them. In quantum field theory, something called a tachyonic mass term can show up in the mathematics, but that usually does not mean a real faster-than-light particle is flying around the universe. More often, it means the assumed state of the system is unstable. It is a signal that the vacuum you started with is not the true lowest energy state, and the system wants to roll into a new configuration. So in serious theory, tachyons often function more like warning lights than like exotic bullets racing past light speed. They tell you the model, as currently written, is sitting in the wrong place and needs to settle into something more stable. That is a very different role from the popular image of a superluminal particle you could detect, capture, and maybe someday use. And that difference matters, because it means tachyons are part of physics in a limited mathematical sense, but not as confirmed objects in nature. After decades of searching, no credible experiment has found a tachyon as a real superluminal particle. High-energy experiments have not found one. Cosmic ray studies have not found one. Neutrino timing has not found one. Astrophysical observations have not found one. The most famous moment that seemed to hint at something like this came in 2011, when the Optical experiment reported neutrinos appearing to arrive earlier than expected, which briefly suggested faster-than-light motion. For a moment, it looked like one of the most solid limits in physics might be failing, but that result did not survive scrutiny. The anomaly was traced to instrumental problems, including a faulty fiber optic connection and timing calibration issues. Once those were fixed, the faster-than-light claim disappeared. So again, when the universe was tested directly, the barrier held. But even if tachyons did exist as real particles, the deeper problem would still remain. They would not rescue causality, they would threaten it. Any usable faster-than-light signal, no matter what carries it, runs into the same issue once you combine it with relativity. Different observers can disagree about the order of events, and that opens the door to messages arriving before they were sent in some valid frame. So tachyons do not solve the paradox, they move it. Instead of asking how a massive object crosses C, you start asking how the universe could stay logically consistent if superluminal information exists at all. That is not progress, that is a new version of the same crisis. This is why tachyons are more revealing than helpful. They show that physicists did not ignore the question. The possibility was taken seriously enough to study. It was examined in theory, connected to mathematical structures, compared with experiments, and pushed hard. And the lesson that keeps coming back is the same one we keep hitting from different angles. Every path that seems to open the door to faster than light motion starts pulling causality toward the edge. The details change, but the danger does not. Sometimes the problem is energy. Sometimes it is instability. Sometimes it is observation. Sometimes it is chronology. But the wall keeps reappearing. So tachyons do not really save the idea. What they do is make the whole issue sharper. They show that even if you try to put the superluminal behavior into a special class of particle that never had to cross the barrier, the universe still does not become comfortable with it. The contradictions do not go away. The observational evidence does not appear. And the theory itself often turns the tachyon into a sign that something else is wrong or unfinished or unstable. That should make you notice a pattern by now. Physics keeps producing things that look almost like loopholes, almost like exceptions, almost like cracks in the wall. But when you look closer, they do not let matter or information casually outrun the causal structure of space-time. And the next section pushes that pattern even harder, because light itself starts doing things that look misleadingly close to breaking the rule, slowing down, seeming to move faster than light in some setups, and creating exactly the kind of confusion that makes people think the barrier is weaker than it really is. This is where the topic gets confusing fast because light itself starts doing things that look like exceptions. You hear that scientists slowed light down or even almost stopped it, and that sounds like a direct hit against the whole idea of a universal speed limit. If light can slow down, then maybe the rule was never that strict. But that is exactly the wrong conclusion. Light can be slowed dramatically in materials. In glass, water, fiber optics, and more exotic lab systems like Bose-Einstein condensates, a light pulse can move far below C. In some experiments, pulses have been slowed all the way down to speeds you could describe in meters per second, not hundreds of thousands of kilometers per second. That sounds shocking, and it is real, but it does not mean the light speed limit is flexible in the way people think. The reason is that the true limit in relativity is not whatever speed a light pulse happens to have in any situation. The limit is the invariant speed c in vacuum, the speed built into space-time and into the causal structure of the universe. When light moves through a material, it interacts with that material. The pulse gets delayed because the electromagnetic wave is being absorbed, re-emitted, scattered and reshaped by matter. So when the pulse slows down in glass or water, you are not seeing the universe relax its speed limit. You are seeing light deal with a medium. The local laws underneath are still relativistic. The deeper rule has not changed. What changed is the effective behavior of the radiation because it is moving through something instead of empty vacuum. That distinction matters a lot because otherwise every headline about slowed light sounds like a loophole, but it is not a loophole. It is more like traffic, not a rewrite of the speed limit built into reality. The photons are not proving that C was optional. They are showing that propagation through matter is more complicated than bare motion through empty space. So yes, light can move more slowly in a material. No, that does not mean matter can now outrun causality. Then there is another case that sounds even more dramatic. Astronomers really do observe things that appear to move faster than light across the sky. Jets from quasars and active galaxies can seem superluminal when measured from Earth. That phrase, apparent superluminal motion, is real and well established. But again, it does not mean matter is actually breaking the local light speed limit. What is happening is a geometry effect. If a jet is moving very close to C and is pointed almost toward your line of sight, the timing of the arriving light can create the illusion that the sideways motion across the sky is faster than light. It is a projection effect, not an actual local violation of relativity. The object is still moving below C where it is. The apparent speed becomes misleading because of how the light from different positions reaches you. This is one of the most important patterns in the whole faster-than-light discussion. Nature keeps creating things that look superluminal from a distance, then turns out not to be. The observations are real. The effect is measurable. The headline sounds explosive, but the underlying causality stays intact. The wall is still there, and then wave physics adds another layer of confusion. Under special conditions, the group velocity of a wave packet can exceed c. That sounds like another direct contradiction. But once again, it is not giving you a usable, faster-than-light signal in the way that would break causality. Physicists have to be careful here, because velocity in wave behavior does not always mean the same thing. Group velocity, phase velocity, signal velocity, and front velocity are not identical. The important quantities for causality are the ones tied to actual information transfer and the leading edge of a signal. Those remain consistent with relativity. So even when a wave packet behaves in a way that looks superluminal on paper, or in a controlled setup, it still does not hand you a machine for sending messages into the past. And that repeated outcome should stand out by now. Slowed light sounds like a loophole, but it is not. Apparent superluminal jets sound like a loophole, but they are not. Exotic wave behavior sounds like a loophole, but again it is not. Physics keeps letting you get right up to the edge visually, effectively, or mathematically. It lets the story look dangerous. It lets the headline sound revolutionary. Then the deeper analysis pulls everything back before causality actually breaks. That is why this section matters. It shows that the universe is not simple, and it is not stingy with strange behavior. Light can slow down in matter. Objects can appear to move faster than light across the sky. Waves can behave in ways that make the numbers look alarming. So the barrier at sea is not surviving because the universe is boring. It is surviving even while the universe is doing genuinely weird things. That makes the limit look stronger, not weaker. It keeps holding even when reality gets complicated, and that sets up the next moment where people thought the wall might really have cracked. Not a projection effect, not a media headline about slowed light, but a real experimental result involving actual particles, neutrinos, apparently arriving too early and threatening to force physics into a rewrite before the measurement itself turned out to be the problem. Then came the moment when physics looked like it might actually be in trouble. Not because of a thought experiment, not because of a headline about slowed light, but because of a real measurement involving real particles. In 2011, the Opera collaboration reported something that immediately got the entire physics world's attention. Neutrinos sent from CERN to the Gran Sasso laboratory over a distance of about 730 kilometers, or roughly 454 miles, appeared to arrive a little earlier than they should have if they were traveling at light speed. And the implication was explosive. If the timing was right, then those neutrinos had gone slightly faster than C. That is why the reaction was so intense. This was not a minor disagreement over details. This was a direct challenge to one of the strongest limits in modern physics. And the reason people took it seriously right away is that neutrinos already have a reputation for being strange. They have tiny mass. They interact only weakly with matter. They pass through huge amounts of material almost as if it's not there. They are difficult to detect, difficult to control, and easy to underestimate. So if any known particle was going to do something shocking, neutrinos felt like the perfect candidate. A confirmed faster-than-light neutrino would not have been a small correction to physics. It would have forced a major rewrite of relativity, or at the very least some deep extension of it. And this part matters, because it shows how science actually behaves when something serious appears. The physics community did not reject the results just because it sounded impossible. It did not say Einstein must be right, therefore this measurement is not worth discussing. The result was taken seriously enough to investigate carefully. That is exactly what good science is supposed to do. Even the most established framework in physics can be questioned if the data really demands it. So for a while this was not treated like a joke, it was treated like a possible crack in the wall. But then the checking got deeper and the whole result started to collapse. further investigation found ordinary technical problems that had extraordinary consequences. A loose fibre optic connection affected timing. There were additional calibration issues in the measurement system. And once those problems were corrected, the faster-than-light result disappeared. Independent experiments including Icarus did not confirm superluminal neutrino speeds. The claim did not survive better measurement, and that is the key point. The idea was not defeated by outrage, or by authority, or by tradition. It was defeated by precision. That makes this one of the best examples in the entire story, because it shows that the speed of light barrier is not protected by sentiment. It is protected by experiments that keep surviving direct attacks. The Optical episode could have been a turning point in physics. For a short time, it looked like nature itself might be pointing beyond relativity. But once the instruments were checked properly, the apparent crack sealed back up. The barrier held again. And this is a very important moment in the script. It reminds us that the faster-than-light question is not just abstract theory. It has touched real machines, real laboratories, real data, and real scientific controversy. Physics did not wave the question away. It put the claim under pressure and followed the evidence. That is why the speed limit looks so formidable. It does not just survive speculation, it survives direct experimental challenge. The Optical story also shows two things at once, and both matter. First, modern physics is fragile in one sense, because very small technical errors can create the illusion of a revolutionary discovery. A tiny mistake in timing can make the universe look different from what it is. But second, modern physics is robust in the deeper sense because the framework only breaks when the evidence keeps holding up under repeated scrutiny. Faster-than-light motion was not ruled out because people were emotionally attached to relativity. It was ruled out because the measurement did not survive the process that real science uses to decide what is true. That is the deeper lesson here. The universe does not owe us a simple answer. A result can look extraordinary for a moment. The media can explode. The public can think everything is about to change. But in the end, it is the repeatable measurement that decides the case. And in this case, once the noise was removed, neutrinos went back to obeying the rule. No confirmed known particle had crossed the barrier. That should push the tension higher again, because now the obvious response is this: if ordinary particles cannot break the limit, then maybe the trick is not to move through space faster than light at all. Maybe the loophole is to let space itself do the moving. And that is where the story becomes even more dangerous, because the universe really does contain something that looks like faster than light expansion. Not because objects outrun light, but because space-time itself can stretch. The next twist is this: space itself is not required to sit still. And that matters, because for the first time the faster-than-light question stops sounding obviously impossible. Up to now, every path has run into the same wall. Matter cannot cross C. Signals cannot cross C without threatening causality. Even strange cases like tachyons do not really rescue the idea. But the universe already contains something that looks like a loophole. Distant galaxies can recede from us at effective speeds greater than light, not because they are flying through space like bullets, but because the space between us and them is expanding. That is a very important distinction. Special relativity limits how fast things move locally through space-time. It does not say space-time itself cannot change. This is one of the places where normal language starts causing trouble. If you say a galaxy is moving away faster than light, it sounds like relativity has already been broken on cosmic scales. But that is not what is happening. In an expanding universe, the metric of space changes. The distance between faraway galaxies can increase because space-time itself is stretching. So when cosmologists say that very distant galaxies recede faster than light, they are not saying those galaxies are locally blasting past the speed limit in their own neighbourhood. They are saying the amount of space between us and them is growing fast enough that the separation increases at an effective rate above c. That fits general relativity perfectly. And this is not a fringe detail in cosmology, it is part of the standard picture of the universe. Hubble expansion already points in this direction. The farther away a galaxy is, the faster it appears to recede because the expansion accumulates over more space. At great enough distances that recession rate exceeds c, this is not considered a crisis. It is a natural feature of general relativity in an expanding universe. Observations of galaxy redshift, large-scale structure, and the overall expansion history of the cosmos all support this framework. So right here, the universe is telling you something important. The phrase faster than light can mean very different things depending on whether you are talking about local motion through space or the evolution of space itself. And if that sounds big, the early universe did something even more extreme. The leading picture of cosmic inflation says that in a tiny fraction of a second after the Big Bang, the universe underwent a period of extremely rapid expansion. Regions of space were driven apart effectively faster than light. Again, not because matter was shooting through local space in the ordinary sense, but because space-time itself was changing. That idea helps explain why the universe looks so flat and so uniform on large scales, and it connects to the pattern of tiny fluctuations we see in the cosmic microwave background. So there is already precedent in physics for distances growing faster than light allows for ordinary local motion. The universe has done it, and that is exactly why this becomes so tempting. Because once you hear that space itself can effectively outpace light, the obvious next thought is, can you use that? Can you stop trying to force a ship through space faster than c, and instead make the space do the work? If the universe can expand space fast enough to separate distant regions superluminally, then maybe an advanced civilization could create a small version of that trick. Maybe you compress space in front of the ship, expand it behind, and let the geometry move the ship effectively faster than light without the ship ever locally violating relativity. That is the basic seduction behind warp drive ideas. This is the first path in the whole story that feels genuinely dangerous in a new way, because it does not start by trying to break Einstein's rules directly. It starts by taking Einstein's deeper theory seriously. Special relativity says no local faster-than-light motion. General relativity says space-time itself is dynamic. Put those together, and suddenly the question becomes more subtle. Maybe the universe does not let you outrun light on the stage, but maybe the stage itself can move, and if that is true, then the problem is no longer just about engines or particles or signals. It becomes a question about whether space-time geometry can be engineered on demand. That is why the stakes rise here. For the first time that the idea does not sound like a direct contradiction of physics. It sounds like a loophole hiding inside physics itself. Not because relativity failed, but because general relativity is richer than the simpler version of the story most people know. And once you realize that, the next question becomes unavoidable. If moving space is the trick, then has anyone actually found a real mathematical way to do it? And if they have, what horrifying price does that loophole demand? Then the question becomes very sharp. Did physics ever produce a real warp drive idea? Not a movie version, not a fantasy engine, but an actual solution from the equations? The answer is yes, and that is exactly why this part is so dangerous. In 1994, Miguel Alcubierre showed that general relativity allows a mathematical solution in which space-time around a ship is distorted in a very specific way. Space in front of the ship contracts, space behind it expands, and the ship sits inside a kind of bubble. Inside that bubble, the ship is not locally racing through nearby space-time faster than light. Locally, it can remain at rest relative to the space immediately around it. But to distant observers, the bubble itself can move in a way that makes the ship appear to travel effectively faster than light. That is why physicists did not laugh the idea away. It did not come from science fiction logic. It came from the real equations of general relativity. That matters a lot. The issue was never that warp drives were too silly to even discuss. The issue was that once you take the equations seriously, they immediately start demanding things that look extreme or impossible or both. So the warp drive concept is not embarrassing because the math is fake. It is difficult because the math is real, and the price it asks for is brutal. The biggest problem shows up almost immediately: energy. Classic warp drive models require negative energy density, often described loosely as exotic matter. That is not the same as ordinary fuel or antimatter or any familiar source of power. It is something much stranger. In some areas of quantum physics, you can produce tiny effects that look like negative energy relative to a baseline vacuum state. The Casimir effect is the standard example people point to. But those are extremely small, tightly controlled effects. They are nothing like the large, stable, usable quantities a real warp bubble would seem to need. Early estimates for the required energy were catastrophic, on scales that made the whole idea sound absurd. Later work improved some of those numbers and reduced the requirements in certain models, but the core problem never went away. Even in the more optimistic versions, the concept stays deeply impractical, and that is only the first layer of trouble. Suppose somehow that you solved the energy problem. Suppose you found a way to arrange the required exotic energy conditions. You still would not be done. Warp bubbles appear to face major issues involving stability, control, and radiation. Some models suggest horizon-like problems, where parts of the bubble geometry create regions that make control from inside difficult or even impossible. Other analyses suggest instability, meaning the bubble may not behave cleanly or survive in a usable form. And then there is the radiation problem, which is one of the ugliest parts of the whole idea. Particles and radiation may pile up at the front edge of the bubble as it moves. If that buildup becomes severe, then when the bubble stops, that stored energy could be released violently into the destination region. In other words, even if you somehow built the thing, it might deliver you by blasting the place you wanted to arrive at. That changes the tone of the entire faster-than-light discussion. Because now you have something that looks like a real loophole in the equations, but the loophole may be booby-trapped. The universe may allow a space-time geometry that imitates superluminal travel from the outside, while also making the engineering requirements so hostile that the concept collapses under its own demands. And this is exactly what makes warp drives so important to your theme. They are not proof that faster-than-light travel is possible. They are proof that the universe can write down something that looks almost like permission, and then surround it with conditions that may be impossible to satisfy safely. That is the reveal here. The question is no longer just, can you exceed the speed of light? The question becomes much more technical and much more severe. Can space-time itself be engineered in a controlled way, using forms of energy we do not know how to produce in useful amounts, while avoiding instabilities, horizon problems, radiation disasters, and possible causality issues? That is a much harder question than most people realize when they hear the phrase warp drive. The phrase sounds like a propulsion upgrade. In physics, it turns into a demand to redesign geometry itself. And there is another reason this matters. Warp drives show that general relativity is rich enough to contain structures that look like shortcuts around the ordinary speed limit. But they also show that every time physics seems to open a door, the next line of calculation starts adding traps. That pattern should sound familiar by now. Near light speed, energy blows up. With superluminal signaling, causality starts cracking. With tachyons, the contradictions do not go away. And with warp drives, the equations may permit the shape, while the required matter and stability conditions make the whole thing almost unusable. So this is not the section where the barrier finally falls. This is the section where the barrier gets smarter. It stops looking like a simple no and starts looking like a conditional maybe that may be even worse. Because a direct impossibility is clean. A loophole with catastrophic side effects is much more dangerous. It gives you just enough hope to keep going, and then forces you to ask whether the price of cheating the limit is tearing apart causality, violating energy conditions, or turning the ship into a weapon. And that naturally leads to the next route people bring up. Maybe the answer is not to drag a bubble through space-time at all. Maybe the answer is to avoid the distance, not by moving faster, but by taking a shortcut through the structure of space-time itself. That is where the next idea enters. Wormholes, not a speed boost, but a tunnel. Then the next idea sounds even cleaner. Do not go faster, just take a shorter path. That is the basic appeal of a wormhole. A wormhole is not supposed to make your ship outrun light through local space. It changes the route instead. If space-time contains a tunnel connecting two distant regions, then the trip can become short even though the places are far apart in ordinary space. So if one mouth of the wormhole were near Earth and the other were near a distant star, you could in principle enter one end and come out the other after a short trip on your own clock, without ever locally exceeding c. That is why wormholes feel so powerful in this conversation. They seem to avoid the speed problem completely, and in one sense they do avoid it. A wormhole is not a faster engine. It is a shortcut in geometry. That makes it conceptually different from trying to accelerate a ship beyond light speed, and also different from a warp bubble that drags geometry around with you. The appeal here is that you are not forcing matter to break the local rules of relativity. You're taking a path through space-time that is shorter than the normal route. So the question becomes, not can you move faster, but can space-time contain a tunnel that makes faraway stop meaning what you thought it meant? That is why wormholes are taken seriously enough in theory to study properly. General relativity does contain solutions that point in this direction. Einstein-Rosen bridges arise naturally in certain mathematical treatments, but that does not mean the useful kind, a stable, traversable wormhole that a ship could actually pass through, comes for free. That is where the situation gets harder. Work by physicists like Morris and Thorne showed that if you want a wormhole to stay open and remain traversable, the equations appear to demand exotic matter with negative energy density. So once again, the math opens a door and then immediately asks for a type of fuel or stress energy configuration that nature has not clearly provided in usable form. That pattern should sound very familiar by now. Warp drives did it. Wormholes do it too. The equations do not instantly laugh at the idea, they allow structures that look astonishing. But then the next line of analysis makes the cost severe. Negative energy is the recurring demand, and we do not know how to produce or maintain the required amounts on anything like the needed scale. Tiny quantum effects are one thing. A stable, traversable tunnel across space-time is something else entirely. And observation has not rescued the idea either. No confirmed wormhole has ever been found. Astronomers do search for unusual signatures, strange lensing effects, and exotic compact object behaviour that might hint at something beyond ordinary black holes. But so far the data keeps favouring known physics. The Event Horizon Telescope has imaged environments around black holes in ways that fit black hole models well. Gravitational wave detections from LIGO, Virgo and Cagra also line up with compact object mergers that are well described by the existing picture. So while wormholes remain allowed as theoretical possibilities in certain contexts, there is no observational sign that the universe is full of convenient traversable portals waiting to be used. But even if wormholes existed, the deeper problems still would not go away. They can threaten causality too. If you move one mouth of wormhole in the right way, especially relativistically, time shifts can develop between the two ends. Then the wormhole can stop at being just a shortcut and start acting like a time machine. The same nightmare returns again. You try to avoid the speed barrier by using a tunnel, and suddenly the issue is no longer distance. It is chronology. Information or matter can end up taking a path that lets cause and effect become unstable. So once again, the bill comes due in the same currency. Not just energy, not just engineering, but the order of events itself. That is exactly why wormholes matter to the story. They expose the real shape of the problem. It may not be speed alone that the universe is protecting. It may be anything that lets matter or information bypass the causal structure that keeps before and after in the right order. Whether the method is a faster ship, a warp bubble, or a space-time tunnel, the deeper question stays the same. Does it preserve causality, or does it let events loop back on themselves in a way that breaks consistency? And that is a big reveal, because it means the universe may be less concerned with how you try to cheat the distance, and more concerned with whether your method scrambles chronology. The method can change, the warning does not. Every route that looks like a true shortcut keeps drifting toward the same danger zone. So now the next possible escape hatch becomes very tempting. If relativity blocks you, maybe quantum physics will save you. Quantum mechanics is already strange enough to make people think almost anything might be possible, especially when entanglement starts sounding like instant connection across distance. But that next hope runs into one of the hardest twists in the whole story, because quantum theory is weird enough to shock you, and still not weird enough to hand you faster than light communication. Then you get to the part that sounds like it should save everything quantum mechanics. If anything in physics looks like it might bypass the normal rules, it is entanglement. Two particles interact separate and later show linked outcomes across huge distances. You measure one, and the other is connected to that result in a way that feels immediate. That is why entanglement gets abused so much in faster than light stories. It sounds like the perfect loophole. No engines, no exotic fuel, no space-time tunnel, just instant connection. And because quantum mechanics is already so strange, people naturally think this must be where the crack in relativity finally appears. And the first thing to say is that the weirdness is real. Entanglement is not a myth, not a misunderstanding, not a science fiction exaggeration built on nothing. Experiments testing Bell inequalities have shown again and again that the world does not behave like a simple hidden classical machine underneath. Local hidden variable explanations fail. From the early work of Alan Aspect to later experiments that closed more and more loopholes, the result has stayed the same. Quantum entanglement is real, robust, and deeply non-classical. So when people say quantum mechanics allows linked behavior across distance, that part is true. This is not fake mystery. The universe really does behave in a way that classical intuition does not prepare you for. That is exactly why this section matters so much. Because quantum theory is not being dismissed here for being too strange. It is being taken seriously at full strength. The correlations are real, the experiments are strong, the weirdness is established. And even after all of that, it still does not give you faster than light communication. The reason is subtle, but the conclusion is very clear. Entanglement links outcomes, but it does not let you control those outcomes in a way that sends a chosen message. That is the part people always want to skip. If you measure one entangled particle, you get a result. The distant partner is correlated with it, but you do not get to decide what your own result will be in a way that encodes information. So the observer at the other end cannot look at their particle and extract a message you intentionally sent. The pattern only becomes meaningful when the two observers later compare their results using ordinary classical communication. And that communication is still limited by C. That means entanglement gives you connection without communication. It gives you correlation without controllable signaling. And that distinction is everything. Because the faster than light dream always depends on usable information transfer. It is not enough for the universe to contain linked events. You need a way to choose a message, transmit it, and have someone else read it before a light signal could get there. Entanglement does not let you do that. It gives you something eerie, but not something you can turn into a superluminal phone. This also clears up a lot of confusion around quantum teleportation. The name sounds like the perfect escape hatch, but it is not. Quantum teleportation does not move matter or information in a way that bypasses relativity. It transfers a quantum state using entanglement plus a classical communication channel. And that classical channel still moves no faster than light. So even one of the most dramatic sounding tools in quantum information theory still stays inside the same causal limit. The quantum part is strange, but the usable message still waits for an ordinary light speed limited signal. Physicists formalize this with the no communication theorem. The name is dry, but the meaning is devastating for faster than light hopes. Entanglement alone cannot be used to send information faster than light. That is not a vague interpretation. It is a mathematical result built into the structure of quantum theory. And this is one of the most interesting places where quantum mechanics and relativity, even though they are often described as uneasy partners, line up on the same side. Instead of quantum physics punching a hole through causality, it ends up protecting it. That is a brutal twist, because quantum mechanics already shattered so many classical assumptions. It overturned old ideas about certainty, locality, and the way physical properties should behave before measurement. If any part of physics was going to hand you an easy, faster-than-light loophole, this looked like the one. And yet even here, with all the weirdness fully allowed, the barrier still stands. That should tell you something important. The speed of light limit is not surviving because the universe is simple and rigid. It is surviving even while the universe is deeply strange. And by now a pattern is impossible to ignore. Relativity gives you time dilation, length contraction, and all kinds of observer-dependent effects, but still blocks FTL. Quantum mechanics gives you entanglement and non-classical correlations, but still blocks FTL signaling. Warp drives and wormholes look like loopholes, then demand impossible fuel or threaten causality. Every path gets close enough to tempt you, then stops right before the point where information or matter could casually outrun cause and effect. So the next question gets harder and more concrete. If faster-than-light motion were actually possible in some hidden way, then the universe itself should probably already look different. Astronomy, high-energy physics, and cosmic signals should be full of clues. And that is where the story turns outward, away from pure theory and toward the sky, because if FTL were real in any useful sense, the cosmos would likely have revealed it by now. If faster-than-light motion were real in any useful sense, the universe would probably look different by now. That's the simplest way to say it. We do not only test physics in labs. The sky is full of extreme events, extreme distances, and extreme energies. High-energy astrophysics gives us constant chances to catch the universe doing something strange. Gamma-ray bursts, pulsars, neutrinos, black hole jets, cosmic rays, all of these are natural stress tests. If particles or signals could really outrun light in a meaningful way, those systems should have started exposing cracks a long time ago. But when we look, the overall pattern is the opposite. The signals we observe overwhelmingly fit a universe where the causal structure stays intact. That does not mean every event is simple, far from it. The universe is messy, violent, and full of timing complications, but the important point is that the complications still make sense inside relativity. We do not see a sky filled with clear cases of information arriving in ways that force us to accept superluminal propagation. We do not see astronomy constantly failing because signals refuse to respect the same causal order. Instead, the big picture keeps lining up with the same limit physics already keeps finding in the lab. One of the strongest examples came from supernova 1987A. When that star exploded in the Large Magellanic Cloud, neutrinos were detected hours before the visible light reached us. At first hearing, that sounds dangerous. If neutrinos arrived first, then maybe they were moving faster than light. But in this case, the timing matched the physics of a collapsing star. Neutrinos can escape from the core much earlier, while visible light takes longer to fight its way out through the outer layers of the star. So the early arrival was expected. And that is exactly why the event was so useful. Over a distance of about 168,000 light-years, even a small, true difference from a light speed behaviour would have shown up very clearly. Instead, the timing placed strong constraints on any large deviation. It became a huge natural laboratory running across intergalactic distance, and it still did not reveal the kind of superluminal behaviour people want. Then there is the broader issue of Lorentz symmetry, which is one of the deep structural principles behind relativity. Modern physics tests it relentlessly. Particle accelerators test it, atomic clocks test it, astrophysical observations test it, precision measurements in many different systems test it. If the speed of light structure were only approximate, if it were some rough rule that broke at high energy or large distance, we might expect to see certain fingerprints. Maybe particles of different energies would propagate oddly. Maybe there would be signs of a preferred frame of reference. Maybe there would be timing distortions that became impossible to explain cleanly. But so far, the evidence has stayed remarkably consistent with relativity. The more carefully we test the framework, the more stubbornly it holds. And that creates a serious problem for any hidden faster-than-light theory. A universe that really permits usable FTL signaling should not be easy to hide. It should leave marks. You would expect odd timing behavior in transient events. You might expect causal anomalies. You might expect unstable vacuum effects, or systematic deviations in precision experiments, or strange propagation patterns in extreme astrophysical signals. The absence of those fingerprints does not mathematically prove that every imaginable superluminal idea is impossible. Physics almost never gives you that kind of absolute closure, but it does raise the cost of the idea dramatically. Now you are not just inventing a clever faster-than-light mechanism, you are also explaining why nature has concealed every sign of it across laboratories, satellites, supernovae, cosmic rays, and galaxy-scale observations. That is where speculation runs into the wall of data. In fiction, you can introduce a loophole and move on. You do not have to reconcile it with supernova timing, with particle beam measurements, with neutrino astronomy, with precision clock experiments, or with the behavior of the expanding universe. Real physics does have to reconcile all of that. And when you force the faster-than-light idea to face the full set of observations, the answer keeps coming back the same way. The universe behaves as if the light-speed barrier is deeply real. That does not make the story less interesting, it makes it sharper. Because by this point, you should feel the pattern clearly. Every route that looked promising either failed in theory, failed in experiment, or failed because it threatened causality. And when you step back and ask what the actual universe looks like, the answer is not a place full of hidden superluminal effects waiting to be exploited. It looks like a universe built to preserve the order of events, and that means there is only one final step left. After all the loopholes, all the near misses, all the strange effects that look like cracks and turned out not to be, you have to answer the original question directly. So what actually happens if you exceed the speed of light? Not in fantasy, not in headlines, but according to everything known physics is trying to tell you. Now the final question has to be answered directly. So what actually happens if you exceed the speed of light? According to known physics, you do not. That is the honest answer. Special relativity does not say it is it is very hard. It does not say it is just beyond current technology. It says a massive object cannot be accelerated to see, let alone pushed past it. The energy required keeps rising without limit as you get closer, and the causal structure of space-time is built around that boundary. So inside established physics, there is no clean moment where a ship reaches light speed and then keeps going. That crossing never happens, and that answer is brutal because it sounds almost too simple after everything we have gone through. We tested the loopholes. We looked at extreme particles, relativistic time, shrinking distance, tachyons, slowed light, neutrinos, expanding space, warp drives, wormholes, and quantum entanglement. Every path looked promising for a moment. Every path either failed experimentally, demanded impossible conditions, or ran straight into the same deeper problem, causality. So when you finally strip everything down, the answer is not dramatic in the usual way. The answer is that the universe blocks the crossing before it happens. But suppose somehow that you did cross it. Then the damage would not just be mechanical. This would not be like an aircraft wing tearing off under stress, or an engine melting, or a hull failing under pressure. The consequences would hit the structure of reality itself. Different observers could disagree about the order of events in a way that stops being harmless. A signal could be received before it was sent in some valid frame. Before and after would stop being universal in the way ordinary physics depends on. And once that happens, the problem is no longer about travel, it is about consistency. A theory that allows effects to loop back on causes starts losing the stable logic that makes prediction possible. That is why faster-than-light motion is so much more dangerous than it sounds. People hear faster travel and think in terms of transportation, distance, or exploration. Physics hears superluminal signaling and starts worrying about chronology, paradoxes, and frame-dependent contradictions. The real threat is not that a ship would go too fast for its own safety. The threat is that cause and effect could stop lining up in a way the known laws of nature can handle cleanly. And look at the alternatives we explored. Warp drives sound promising, but they seem to require exotic matter, negative energy, and a level of space-time engineering we do not know how to achieve, while also raising stability and radiation problems. Wormholes sound cleaner, but they also demand exotic energy conditions and can drift toward time machine behaviour if you manipulate them the right way. Tachyons remain unobserved and do not solve causality anyway. Quantum entanglement is real and strange, but it refuses to carry usable faster-than-light messages. Cosmic expansion proves space-time itself can stretch in ways that beat naive speed language, but not in a way that lets your ship casually outrun the causal limit. So the loopholes are real enough to study, but every one of them comes with a price so severe that the escape route keeps collapsing, and that leads to the deeper reveal at the centre of the whole story. The shocking part is not that the universe has a speed limit. A universe can have limits. That alone is not strange. The shocking part is that this particular limit seems tied to the consistency of reality itself. Light speed is not just a cap on how fast something can move. It is tied to how time, space and cause fit together. It is one of the rules that keeps different observers inside the same coherent universe. Once you start pulling on that boundary, everything connected to it starts straining: energy, time, distance, simultaneity, chronology. So what happens if you exceed the speed of light? If modern physics is right, you never do. And that may be the hardest answer in the whole script, because it means the universe is not stopping you just because the engineering is not good enough yet. It is stopping you because beyond that line, the idea of a stable, shared reality may start to fail. The barrier is not just protecting a number on a speed scale, it is protecting the order of events itself. And that is the final twist. The speed of light is not important because light is special. It is important because reality seems to be built around it. Cross that line, and you do not just risk breaking a machine. You risk breaking the rules that let the universe make sense at all. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.